In this class, we will discuss how we use the multiple regression equation when all variables are in their standard score form or their raw scores are converted to z-scores. When scores on the predictors and the criterion are in their standard score form, the basic multiple regression equation changes to zy hat is equal to beta times the z-score for predictor 1 and beta times the z-score for predictor 2 and so forth. In this formula, zy hat is the predicted z-score on y, and the regression line once again connects all the predicted z-scores for y when we use z-scores for each of the predictors to make our prediction. Also, the constant disappears from the standardized multiple regression equation because the regression line passes through the origin of the graph. Remember that for any set of z-scores, the mean is equal to 0. Thus, the y-intercept is also 0 when the z-scores of all predictors are simultaneously equal to 0. In the standardized regression equation, the name for beta changes from the partial regression coefficient to the standardized partial regression coefficient. It is used to multiply or weight z-scores on x in order to predict z-scores on y. Another important way of thinking of beta is that it equals the change in the predicted z-score of y when the z-score of x increases by 1 z-score. Of course, when we are talking about a 1 unit increase in the z-score for x, we are actually saying that the raw score of x has increased by 1 standard deviation. We are able to use beta to assess the relative importance of predictors. To see how we do this, let's return to the table from the previous class. Notice we have added a new column that reports the beta, or the standardized partial regression coefficient, for each predictor. Also notice that the constant is missing from the column for beta, as the intercept is not part of the standardized multiple regression equation. Although we can test hypotheses concerning B and determine if a predictor is a significant predictor of y, we cannot use B to compare the importance of one predictor relative to another. This is because it is computed based upon the raw scores of the predictor and the criterion. However, predictors can use many different scaling strategies. In our example, intimacy and anxiety are measured on interval scales with different ranges, while income is measured in thousands of dollars. This problem is addressed when we compute the standardized partial regression coefficient because all predictors now share the same scale, which is the z-scale. Let's continue our discussion of beta in our next slide. In most cases, we will say that predictors with larger beta tend to make a greater contribution to the unique prediction of the criterion relative to other predictors in the model. Thus, even though the B for income is smaller than the B for anxiety, because the beta for income is larger than anxiety, we know it has a greater impact on predicting someone's score on life satisfaction than will anxiety. Similarly, we can also see that income has a larger beta than intimacy. Thus, while they are both significant unique predictors of the criterion, based upon the beta, we would conclude that income plays a more important role than intimacy in determining the final z-score. One caution about this way of looking at beta is that B and betas for predictors are totally dependent on the other predictors in the equation. If we were to add or subtract predictors from the model, then the unique areas for each predictor would be likely to change, and so will their B or beta. For example, if we added a predictor such as social prestige to the equation, we might find that the unique area predicted by income is dramatically reduced, while the unique area predicted by intimacy increases. Such a circumstance would lead to different B's and different betas and cause us to adjust our impression of which predictor is more important in this model. Other statistics are used to assess the relative importance of the predictors, including the partial correlation coefficient. A discussion of this topic is beyond the scope of this course, and I will refer you to your text for a further discussion of how to interpret this statistic. Another important issue in multiple regression is how a model is built, or how the equation is computed. There are many ways to add predictors into a model that range from adding them in all at once or adding them in a sequence in stages. When predictors are added in stages, researchers will evaluate the model at each step or stage of the process. A complete handling of this topic is also beyond the scope of this course and really should be discussed in the context of research design or the type of research question being posed. Your text has a discussion of various multiple regression models. Finally, multiple regression models can include categorical variables as predictors and evaluate their effect on the criterion right alongside the contribution of predictors using interval or ratio scales of measure. This makes multiple regression a very flexible procedure and is one of the reasons its popularity continues to grow in the statistical literature, while formal means tests are used less frequently than they were in an earlier time. Again, a complete handling of this topic is beyond the scope of this class, but you can look forward to learning about these more complicated models in further classes on statistical methods.